I'm not going to yell this time.
I was waiting for it.
Last time I was just super hyped. I pounded a Red Bull. We went live. The intro was super loud. I just couldn't help myself. So I'm not going to scream this time. I hope you guys don't mind.
It's okay. We'll let it go this time. How's everybody doing?
Good. Welcome, everyone. Episode 2 of RTVcron. We are back again. We were here last month. We do this every last Thursday of the month leading up to DEF CON, where we bring in someone to do a workshop and talk through some offensive security tactics, and hopefully you learned something. So episode 2, really looking forward to it. Of course, I'm Corey Wolf. We got good old Mike Hacks Things, and my friend and yours, DSync.
Hey, what's up?
Here we are. So we got some pretty cool stuff going today. I mean, of course, DEF CON is in DEF CON planning is in full swing for us.
Yes,
Red
it
Team
is.
Village, like nonstop. Call for villages, call for volunteers, workshops, tactics, sponsors, you name it. We got it going on right now, and everything's pretty much open. So, Mike, DSync, what are we doing? What's going on? We doing anything? Or are we just hanging out?
Yeah, I mean, a little bit of hanging out too. I'm going to stick around for this workshop here with Kevin and Skyler. I do have a little something special here for today. As people may know, we have our typical Red Team Village logo, and then every year we have basically a themed mascot that we use. We give away stickers, we give away patches, we basically paste it on everything. And we have a new one for this year. And I figured what better place to reveal it than here on Cron and announce a couple other things that we have going on. So I'm going to attempt to do this without breaking things, which is going to be a challenge.
No, Mike's pushing buttons.
And
we're gonna share the screen.
We're gonna see here.
All right, let's see how it works out.
Let's see how it goes. Oh, here we go. I made a little video clip. I am not a video person, so this is literally like a clip in one transition. So here we go for the 2025 RTV mascot reveal. There's no music, so it's going to be kind of, a letdown. But...
Well, can you just go down?
No, I can't do that. So this year, we've done, in the past, we've done some gaming themes. Last year was Halo. The year before that was it was Fallout, I believe. This year we're going back a little bit to, a little bit of the 80s retro theme. We're going with a Tron theme, which actually is super relevant because there's a new Tron movie coming out this year. And we honestly
we didn't know that.
We did not know it at all.
Totally got lucky.
The amount of excitement that I had after we realized that there was going to be a Tron movie and how perfect it lines up with that. So this is our mascot. In conjunction with the reveal of the mascot, as we've done in the past, we have a few competitions going. So the first is that on our Twitter/X page, we will be posting, a little contest revealing the mascot, and we need a name, right? So we're going to be accepting name submissions for our mascot for this year, as we've done in the past. Prize for the most voted on name, or the one that evokes the most happiness within us. So we're gonna have some swag, some special things for that. Also for the the spreading of this information. Who if anybody likes and shares and does those things, we're going to be picking somebody there also for some prizes. The caveat there is that we do request that people are going to be at DEF CON 33 in order to claim said prizes. So there we have it, the mascot for 2025.
One more time.
Question in chat about challenge coins is, that's going to be what we put on the challenge coin. That's going to be what's on our t-shirt and other associated things.
All the swag.
Cool
it'll
things.
be our coins. It'll be patches, shirts, bags, whatever else we can find to plaster that logo on. We will be doing so. So there we go.
Yeah. Very good. Well, come on. Can we see it one more time? Let's see it one more time.
Oh, you're going to make me try and reshare again. Okay, hold on.
You didn't close the window, did you?
I didn't close it, but here we go. There we are. It's still open there. There we are, our Tron mascot. And For those who are very adept and can see much better than I can, instead of the halo or the disc, we have him holding a Unify AP. So it's kind of in theme, but also with our little twist for RTV stuff. So we added the little blue ring there for our little Unify AP. So yeah, hope everybody likes it. If you don't, sorry, but it's still going to be on all of our stuff.
Yes, yes, it is. If you don't like it, too bad. That's what it is. That's what we got. Yeah.
And yes, we've had temporary tattoos in the past.
Oh, maybe we will again. I don't know. Not making any promises. Not making any promises. Yeah, that's awesome. I think I was so happy that it worked out with Tron and everything. And then yeah, it was funny because like we decided on it, and then someone posted in our chat, "Hey, there's a new movie," which I will say it does. I mean, I think it looks pretty cool, the new movie, but we'll see. You never know.
That's going to be a big bummer if it's a huge flop or whatever, and we like totally invest. But at least we went the retro theme, so we're going back to the originals. And some people might have guessed that was going to be where we went with a few of our latest posts there. Krista on our marketing side has been going full out with the Tron theme so far. So a little bit of a allusion to that mascot. And yeah, we're excited to finally unveil that, and now we can post it, move forward, and start thinking of some names so you can win some prizes here.
Yeah. So we got that going on. Of course, we do have our call for volunteers, our call for workshops. So if you want to do a workshop like what Kevin and Skyler are doing here today, if you want to do one at the Village at DEF CON, the call for workshops is open. We also have the call for tactics open, which the tactics are basically an activity that could be there for a few hours where people can sit down, maybe spend 10-15 minutes hacking away at something. That's new to the Village this year, so our call for tactics is open. Call for sponsors as well, so those are only open for another few weeks actually. So if you have any interest in sponsoring, volunteering, or doing a workshop or tactic, please make sure that you go to redteamvillage.io. Where you'll be able to find all the information that you need to participate. So we're getting pretty hyped. It's only April, but like we said before, we are in full swing planning. Yeah, just if you want to get involved, redteamvillage.io. So.
And if you're looking for a good way to get more comfortable in front of people in a teaching capacity, these little tactics are great. Small crowd, people flowing through. You don't have a class sitting at a table staring at you. So really low pressure environment to learn how to teach other people.
That's a good point. That is a very good point. I didn't think of that. So yeah, for sure. Good way to get your foot in the door. No question. So.
Yeah, and it's one of the things that came out of the feedback we received last year, the way that we ran things. So it's going to be, the Village is going to be really heavily focused on that training, on that education aspect, right? We're going to have basically workshops, some panels, tactics, and those tactics are just going to allow people to flow through the Village, not have to hopefully wait in line too long, right? So if you're thinking about trying something, maybe you have like a little nugget of information you want to share. Tactics a great way to get some feedback on that, right? Have somebody try it out, answer some questions, kind of guide them through that, and get some feedback on what you're doing there. And hopefully, it allows more people to come, stop by, say hi to us, say hi to all of the presenters, all of the speakers. And yeah, based on the planning that we've seen so far, I am very excited about our space this year. Haven't finalized anything yet, so once we do have more information to share, we will of course let you all know. But as it stands now, it's looking like it's going to be one of our biggest years.
Yeah, it is. Yeah, it is. All right, cool. Good reveal. I think I hope everybody likes the logo. Like Mike said, if you don't, too bad. It is what it is. It's too late. Things are getting printed and planned out and sent out, so it's happening. It is what it is. I think we can probably bring our speakers in here in just a minute. But before we do, Mike, Desync, anything else you think we should talk about?
I don't think so.
I don't have anything.
No? Okay. All right.
I'm excited to learn.
Me too. So on that topic, let's bring in Kevin and Skyler. So here we go. Let's see. Oh, he was sharing screen and screen. There's Inception, screen Inception. No, I like it. So Kevin and Skyler are here today to do a workshop. They have some slides as well, which we will share the link to those slides in the chat so you can check those out as they're going through their workshop. Today they're going to be talking about malware and interesting ways to do payload creation. So just want to say again, Kevin and Skyler, we appreciate you guys taking your time here and giving back to the community like this. We will in just a minute here, me, Mike, and Desync will drop off and hand things over to you. But just want to say thank you again. We appreciate it. We know that people get a lot out of these, so thank you. We're going to drop off. If you need anything from us, just give an AO, and we'll hop in and help you with whatever you need. We will also be monitoring the chat, so if you have questions or you want some clarification on something, just post in the chat, and we'll make sure we hop in and let Skyler and Kevin know. But other than that, Kevin, Skyler, it's all you.
All right. Thanks, Corey. Appreciate the opportunity to present. I'm going to be talking about malware, or Skyler and I are going to be talking about malware. Both of us kind of live in the red team space a little bit. So malware is a bread and butter tool that we have to rely on as part of our daily operations. So I'm going to give you guys some tips and tricks that we've figured out from our day jobs and just kind of tinkering around and stuff. So this is my Who Am I slide. My name is Kevin Clark. I'm on the targeted operations team at TrustedSec. I work with a bunch of great coworkers who are all smarter than I am. So it's a really a great place to learn things. And some of this is stuff that we've, figured out internally on our team. I also teach. I like Active Directory and payloads, obviously. So I teach 2 courses on AD and payloads for Black Hat, DEF CON, other conferences as well. So if you like what you see here, I do teach classes. So that's an option if you want to learn more. And then I like playing volleyball. I'm really trying to work on my approach right now and figure out how to get the perfect spike. So that's what I'm doing outside of work.
Excellent. Yeah, like Kevin said, we're both red teamers at heart and are in and around this space a lot. And we would love to have had something like this when we were first going through. And we're definitely just standing on the hills of giants or the shoulders of giants and just trying to pay it forward. This is my Who Am I slide. I'm an independent security researcher at the moment. I'm looking forward to trying to present at DEF CON and Black Hat again this year. Kevin and I are putting together some other tools and offensive security tooling that we've open sourced and have submitted to Black Hat and DEF CON. So we're super excited to hear back on that, and hopefully we'll see you guys there. In the past, I've also written a various amount of Python tooling, and have unfortunately been forced to write C# because sometimes you have to write things for Windows and do things on Windows. But on the side, I also do a lot of golfing. I'm definitely a golf addict. I'm constantly trying to work on, not slicing the ball as much, but, maybe someday I'll be, play professionally or something. But this is pretty much what I do day in and day out. So I hope you guys enjoy what we're presenting, and I look forward to seeing you guys at these conferences.
Sweet. Okay, this is my table of contents slide. We have a couple of things we're going to talk about, different sections. This talk goes over the life cycle of payloads. So from the very beginning of the payload process all the way to the end. And then we're going to go in depth on each one of those. I call them links in the chain. Basically, each step of the way, there's some things that we want to understand and know what to do and what not to do in each step of those of that chain. So this, in my opinion, is the most important slide in the slide deck. I have this thesis that hopefully by the end of the talk I can convince you of this, that payloads are fundamentally easy to bypass EDR if you look at each individual link in this chain. But the difficulty happens when you combine all of these. So you can think of you can think of writing malware or generating payloads kind of like playing a game of Minesweeper. It really is easy. All you have to do is not, step on a mine, right? And so the difficulty comes in when you try to do this on a larger scale. You have each of these steps. And so we're going to go through each one of those steps and hopefully give you a better systematic approach of how to build malware, what not to do for every single step of the way. Okay, so we start with the very beginning here. We're going to talk about how do you get a payload into an environment. This isn't exhaustive. We don't have time to cover like every single detail about this, so I'm just trying to give you my kind of top few tips for each one of these steps. So at a basic level, when you're downloading malware onto a host, there's a couple things that we're going to want to avoid, basically, or defenses that we want to avoid. The first is the browser itself. If you're using a browser to download, if you see my screenshot here, you can see that, for example, exe downloads are blocked. This can be configured in things like group policy to block other file types as well that may be malicious. The web gateway. So this is something that is going to prevent an endpoint from accessing certain websites or URLs on the internet. So there's some considerations there with that. And then finally, the firewall itself. So for example, if you try to download maybe something super well known like a Interpreter executable, your firewall is going to be able to read that data and say, oh, there's a download for this known malicious tool. I'm going to block this, right? And we see that too. It's a lot harder than it used to be. We used to just be able to email EXEs and attachments, believe it or not. But time has passed, and we have to become a little bit more sophisticated about how we deliver malware to endpoints for like something like a phishing simulation exercise or a red team engagement. So the first thing I'm going to talk about is container formats. These are really big right now. You see, instead of sending executables, you're going to send zip files or 7Z files or something like that. Basically, these containers are just files that contain other files. So I think it's pretty common, at least on my red teams, instead of sending an exe or whatever, we'll just send a password protected zip file and then give instructions on how to unzip that, and then the victim will go through the process and then kind of get that final payload file out. But now we avoid sending a raw exe through email or even downloading an exe in the browser. So if you know anything about like zip files, that they can be encrypted, which is cool from an attacker perspective, and we do that. You can also mask the file names on zip files using encryption. So if you use something like 7-zip, you can encrypt those file names inside of the zip file, which can be useful for anti-analysis. And then something that's been successful for us is Windows 11 now supports 7-zip archives natively as of a recent release of Windows 11. So it's not a hit or miss to send 7-zip files to targets anymore. You can send them and basically assume that they'll be able to extract them, which is really cool. Another technique that we use a lot for our red teams and phishing simulation exercises is we'll use these different file formats. So everyone kind of knows about the standard like exe, DLLs, PowerShell files. Maybe if you're a little bit more familiar, some of these like VBScript and JScript and VBA files. A lot of those are starting to get at least on our more mature clients, we find that these file formats are commonly blocked, not, won't be downloaded or have preventions even to prevent them from executing. And so we're starting to have to find additional file formats that can be useful here. So I listed a couple cool ones that you may or may not know of that we either have in the past or currently do use for our operations or phishing exercises. Stuff like Java jar file. I mean, this is pretty old, but hey, guess what? You can send people jar files over email or have them download jar files and then run them. If you know your target has Java installed, that's a great way to get code execution. My coworker Oddvar has this tool called Specula, which we released recently, which generates these reg files, which are registry modification files, which is really cool. I never would have guessed or figured out that you could use a reg file as a payload, but it goes through and it sets up Outlook to function like a beaconing C2. We have some blog posts on Specula as well on the TrustedSec website if you're interested in checking that technique out. But that's definitely a cool one too. So there's a whole lot of these weird file formats that you might be able to use for some of your operations that you just have to discover.
Hey, we had a quick question about your container techniques.
Yep.
Actually, from Mike was wondering, does the container technique used have a noticeable impact on success? Are you more successful with zip files versus 7-zip files? And I think you mentioned that sending zip files is problematic.
It can be. I think zip files are pretty well known to sometimes be malicious. It depends on the client, I guess, or the controls in place. Certainly it's better than sending a regular EXE or a DLL or something. But yeah, we're starting to see, people move away from sending encrypted zip files. Although if you're doing something like an assumed breach where you can just download a zip file, I still use zip files a lot. You'll just pack your payload inside of a zip file, encrypt it, download it from some Azure blob or other endpoint, whatever, and then unzip it on your own machine. So it's a lot easier if you're able to do those actions yourself. But it can be hard to get social engineering success with zip files for sure.
And did you notice any difference in different container techniques, or did you just use the one you were comfortable with?
Honestly, it's very subjective. So I talk to my team a lot about, hey, what are you guys having success with? Do you like zip files? Do you like 7-zip? Do you like, VSTOs? Is everyone still using reg files? It kind of ebbs and flows. Some people like reg files a lot on my team, and some people like, I don't know, VSTOs or whatever.
Sure. Yeah.
And yeah, it just, I try to use whatever people like the most, if that makes sense, whatever people think is going to work. So,
okay. Thank you.
Yeah, for sure. Let's go to the next question or next slide here. So, HTML smuggling, this is kind of an interesting concept. This is not new. I guess I should say nothing in this presentation is new. That's another reason I'm doing it. Is because I feel like a lot of either red teamers or people who are getting into the space don't know the basics 100%, and I think the basics are really important. So I actually also believe that to get payloads past modern EDR, you actually don't need any novel tradecraft. If you just implement things correctly and take care in how you build your payloads, you can use old school tradecraft the whole way through. And that's, to some degree, that's what we do at work. So HTML smuggling here. On the right side, I have this screenshot here. This is basically JavaScript. It's code that will pack a file into JavaScript and then download that in the browser instead of the file here. When it goes over the wire, it's kind of encrypted in this HTML format instead of just being sent directly over, an HTTP connection. This is, again, an old school technique, but still can be effective depending on, specifically for evading kind of that SSL stripping, the web gateway, right, that might be inspecting traffic in or out of a corporate network. So this is probably a bad example of it, right? It's pretty obvious what this does. You see some XOR decryption going on and then creating this new blob and having it download. But you can get very creative with your HTML smuggling implementation such that the network device, the firewall usually has no idea what's being downloaded here. So that brings us to our first exercise. We're gonna do some stuff with zip files, and then we're gonna use a tool that I wrote recently that does this HTML smuggling to basically download a file, simulating what a phishing victim might see when they downloaded your payload. So yeah, I have 4 steps here. So first we're going to use 7-zip to generate a password protected zip. I'm going to take an exe file on my Windows computer. Imagine that this is your payload, but it's maybe any exe file or something. We're just going to pack it up inside a zip file. We're going to password protect it, and then I'm going to serve it here on this web server that I've written that does HTML smuggling, and then I'm going to download it in Chrome and Firefox, and then I'm going to decrypt it, and hopefully I should get the original exe back. So over here I have my Windows machine. I'm going to be using this Windows machine throughout the presentation for some of the demos. It's just a Windows 10 machine. That's nothing special. So the first thing we're gonna grab the. Can everyone see this all right? Can you guys see the Windows machine here? Is this legible?
Hey, yeah, it is. You're just the audience is delayed from. You're not going to get quick feedback.
Okay.
It's like a minute or 2 delay.
Great. That's okay, I think. So I'm going to use the Notepad executable here, just as the demo file. I'm going to paste this over here. So I already have 7-zip on here, I think. Actually, maybe I don't. We can use, I'm going to do this on my Mac here. So I'm going to go over and take this Notepad file, and we should be able to do 7z on this. And I think it's encrypt, and then it should be something like this. Let's see here. I'm actually going to go download 7-zip on this machine really quick because it's going to be easier. But so you need 7-zip to encrypt files. You don't need 7-zip to extract 7-zip files, which is really cool. So we only need 7-zip here to actually generate these files. Great. So we're doing live demos here, so you guys are going to see me struggle a little bit and mess things up. We're going to do add to archive, and then we're going to do password. I'm just going to do test. Here's password. Then we should have this file afterwards here. Great. So now this is encrypted with 7-zip and it's packed up. Now I have this notepad.7z, and then I'm going to use this this tool I have called NotUpdog. It's I had to kind of rewrite some of the. There's a Python tool called Updog that will serve files, and in this case, this one will just will also serve files, let you upload and download, and then it does HTML smuggling for the downloads as well. So we're going to do that and then run this. HTML smuggling mode is enabled. Let's see here, and then the link is in the slides here as well for this tool if you want. And I think it should be posted in chat too if you want to go take a look and follow along with this exercise. So, all right, I should be able to grab this file from my Windows machine now. Here's my IP address. And then if I go to this IP address, you should see notepad.7z. So this is the file that we've encrypted here. And then when I click on it, it's gonna say preparing download here, and then it's gonna download this file. I really actually want to I want to view the source of this page, view page source. So you can see here that this is that HTML smuggling code where the page itself is just this blob of JavaScript here, and the payload is shoved in this base64 blob, and then it gets encrypted with a key, and then decrypted here, and then actually once it's decrypted, finally uses a JavaScript click element to basically emulate a click or a download of this file, and then ultimately this gets saved here. So now I have this 7-zip file, and I should be able to extract it with the password of test. Extract files. It says password. I'm going to say test here. Click OK, and then I should have a new this notepad binary is here. So that's how you can encrypt and upload or download a file depending on which direction you're going, I guess. That maybe you shouldn't be able to be allowed to transfer to a host, right? Great. That was the demo. Any questions on that? Or we'll move on, but if there's any questions on the demo, we can answer those as we go.
Excellent. One note on the payload delivery stuff when we were talking about the bespoke file formats. One of the other things that we like to use in our discretion is really like who the target is. So if the target that you enumerated was like a developer, you could try to target VSTOs or file formats for applications that you know probably are on their desktop. Reg files are really nice because they're going to work always, not in the sense of evasion, but just in the fact that there's going to be something that will be able to launch them. So being able to use that kind of discretion is also great, and just utilizing your open source intelligence so that you can more accurately deliver payloads in whatever file format you'd want to target. Taking a little bit of a pivot, talking about payloads at rest. When we're looking at the file format after it's been delivered, there's a couple other detection mechanisms that EDRs and other detection tools can use to be able to pick off our malware, unfortunately. So this is just one other link on the chain that we have to make sure that we're paying attention to. One of the first things that we look at is really what is living unencrypted and clear text inside of the binary. So there's plenty of different strings that you can pull from a binary. Typically what we'll see with like .NET binaries is like the manifest or other kinds of strings that indicate what it's importing. Along with this, if you start to do like AMC bypasses, one of the common detection mechanisms is looking for a specific byte string that would be stored within your binary that would be used for an AMC bypass. So just knowing that EDRs will be able to see this and be able to ingest this and use that for detections is good to know about, because we can do some sort of deobfuscating or obfuscating to make sure that they can't pick those off. Along with this, they can also start to do a little bit more advanced analysis with imported APIs. So all applications will have to essentially allow the operating system to see what APIs they're going to import, so that once the image gets loaded into memory, it'll be able to make and link all the references necessary. With that, EDRs can also do the same. They can look at what APIs you're importing. So there are common APIs that are used for things like shellcode injection that we'll talk about that can trigger some type of detection. On top of this, there are also things known as code signing and other types of signature detection that will essentially take large portions of the binary and basically build a hash for it. And a lot of these EDRs, as we'll talk about, are glorified signature databases. Maybe I'll get a little bit of hate for that, but essentially they're looking for very common sets of bytes within these applications. And if X amount of bytes are listed as known malware, such as like things like how VirusTotal is working, they'll flag that and sometimes not even allow it to execute. They'll just delete it from the system once it hits disk. So we'll talk about that in a little bit more detail, but we can go ahead and move to the next slide. So this is talking a little bit more in depth about these static signatures. So like I mentioned before, a lot of functionality within common EDRs is very reliant on static signatures, even though they might claim otherwise. There's essentially a zero tolerance policy for EDRs to kill legitimate applications from a business model. So this essentially forces them to have to rely on things that are highly likely to be able to detect whether or not something is actually malware or not. Think if you were to pay $20,000 for one application to be running in your environment or more, and then it was going around killing a bunch of legitimate applications. And fortunately for us, a lot of applications, even to this day, that are legitimate business functioning applications use things like process injection and reflection. So sometimes those heuristic analysis capabilities have to be tamed down a bit. And one of the things that they'll have to use is signature detection. So like mentioned before, this is essentially some hash built out on X amount of bytes. And if it's been detected, it will then kill or delete the binary off of disk. One thing that we can use here, which is very popular, is Defender check. Essentially, this allows us to use Defender to scan the binary and identify bad bytes. So once it's detected that hash of bytes, it'll say, hey, like these ones are definitely known malware, and that you'll have to start going through and trying to remove that. So you can go through a sequence of running Defender check against your malware, and once you are able to go through and run it across different portions of the application, you'll be able to narrow it down exactly what bytes are triggering that alert, and then adequately remove them. So very common technique that we use across definitely different types of pipelines for our malware development, and definitely very, very useful. Another thing, I guess, as well, that kind of drive the point home, even detections like DLL injection, for example, or DLL hijacking, will also use things like signature detection on the back end. So think, for example, if you're finding an executable that is loading a DLL through its DLL resolution process, and you find that you have write access to that DLL, you can write to it. And once the process executes, it'll essentially load that DLL, aka why it's called DLL hijacking. EDR, including things like MDE, will essentially have a list of known hashes and signatures for DLLs that are already shipped with Windows. So think things that are in C Windows System 32. And if you find a DLL hijack for one of those, it's great because you'll be able to get code execution. But a very common technique is once MDE is able to find that DLL was hijacked and being loaded into the process, it'll check whether or not that DLL signature was matching the one that was in System Windows 32. Essentially, it's glorified database. And if it doesn't match or if it's not signed, then it'll just kill the process and trigger it as a DLL hijacking technique. So just building that picture of having that entire mindset while you're going through and developing these pieces of malware, so that you'll understand that this is the kind of capabilities that EDR have. We can go ahead and move on to the next slide. Yeah, and talking a little bit more about the API imports. So when a process is loaded into memory, like we said at the beginning, it'll have to then expose its APIs to the operating system so that it'll know what things and what DLLs that it'll have to have handles for. So one of the tools that we like to use, and we'll demo this later, is EXE-Spy, that essentially do the same thing, which EDRs can do as well, where it'll look at statically on disk what APIs this image is going to want to have before it turns into a process, or have access to before it turns into a process. In particular, there are certain APIs that can be leveraged to create memory and turn that memory permissions around so that we can then use it to execute shellcode in memory. That's typically very suspicious. A common technique that's used nowadays is to use alternative APIs that will then sooner or later call the desired API, but not in a direct fashion. So that you can do something known as indirect API calls, so that you will be able to evade the more basic detections of looking for API calls like virtual protect. Another one that's great is file metadata. So think you just wrote your excellent malware. You were able to do your awesome HTML hijacking technique or smuggling technique. You're able to get the malware into the environment. Everything's nice and sound. But you forgot that when you compiled your C# executable, that it was going to mark it as a compile date of today. So this is one of the properties of what your binary can have once it hits disk, and definitely a very well-known technique from EDR to be checking is what compile date was your binary, was it signed, does it have other properties of a legitimate executable from wherever it's running from. Thinking about just different ways that you can essentially make your malware look more legitimate is really the home base for malware development. So looking at if you can do some type of enumeration on the system prior to delivering your malware, figuring out what processes are running on the system, where are they running from, what legitimate information can you use, is definitely very, very useful. But then some other things like the time date stamp, we can actually modify ourselves. So in most of our payload pipelines, what we'll do is we'll set it to some legitimate date that wasn't today, maybe a couple of months ago, or maybe even a year ago, just to kind of thwart any of those EDR detections, so that we can at least get to the next chain in the process. Excellent. This is definitely something that we got caught with at some point. So we were definitely going through the chain, had our excellent malware that we were very proud of, and sooner or later it got detected and had no idea why, because we had packed it, we had developed it, we changed all the properties about it, and then ran into something like this. So what Entropy essentially is, and we'll talk about how it plays a role in malware here in a second, is essentially a method in detecting the randomness of a program. So think that you just packed your malware, you encrypted it, you have it at a blob stored in your binary. What that's going to look like, especially if the unpacking code is very much smaller than the packed binary that you're actually trying to launch, is it'll look very random. So the entropy will essentially be super high, aka the screenshot on the left. However, if you have essentially no randomness at all, it's very predictable. Essentially the screenshot on the right, where the next ASCII character is going to be an A, you'll have completely uniform. No one is better than the other. What we're actually looking for here is like I mentioned before, is going back to that legitimacy home base. We're trying to figure out what legitimate programs typically range in between. And from our research, we've typically found them to be around 4.5 to 6.0. So jumping between super random, not random, and averaging out around that 4.5 to 6.0 range. So with that, we're actually able to go through and add different types of business words essentially to our binaries to make sure that they fall within that legitimate range, because our packed code, since it's much larger than the rest of the code itself, actually it spikes that randomness counter all the way up to about 7.0, so outside of that 4.5 to 6.0 range. And that is definitely a trigger for EDR saying like, hey, this is definitely a packed payload. So you can see here on the right, we have a bunch of payloads that are within that 4 to 5 range, where it essentially is an unpacked entropy. It's standard. It's not screaming anything like this is definitely super random, and it's random for a long period of time. Whereas on the right, we have almost borderline 7, if not 8 at some point. This is definitely some binary that it has a small amount of unpacking code with a long array of packed code that is super random. Think base64 or AES encryption, just that long encrypted or encoded blob of text. So, and this will make more sense in this next screenshot. So quiz time. Based off the information that I've explained, I think what binary here based off of this graph would be considered a packed binary versus which one is not a packed binary. And maybe we'll give like 30 seconds for, well, I guess we have like a 2-minute delay, so maybe a minute, and then I'll start explaining it, and then I'll see the comments.
That 2-minute delay was on my end. I refreshed my other tab, and it's actually like 15 to 20 seconds, so it's not that bad.
Excellent. I do see comments rolling in already, so that's good. That's good news. Yeah, and that's exactly correct. So that first one there is definitely the packed binary. I that definitely makes me feel better, because that means I explained it in at least somewhat of a functional manner. But yeah, definitely the top one. And the reason being is because we're seeing that long array of super random bytes. Essentially what you're seeing on the left-hand side is what the entropy came in as, and think, remember back to higher entropy equals more random, lower entropy equals not random. So since we're in that 6.5 to 7 range for a long period of time, that blob that you're seeing there is most likely some type of packed or encrypted code. The bottom one is definitely a legitimate binary, because as it has some high randomness to it, it stays within that 4 to 6 or 4.5 to 6 range. And at the end of the total average, you'll see something probably around 5 for that second binary. So fortunately, entropy is actually...
We have one question. You may get to this, so tell me if I'm too far ahead, but someone asked, do you have a tool for calculating that entropy?
We do. I'll leave it up to Kevin to answer the rest of that question, because we definitely have a slide for that that we're excited to share.
Okay. All right. Perfect.
Yeah, we'll get there. There's a little script that I've written that I'll link to in a bit, but there's also a bigger tool that handles this for us too.
Excellent. Yeah, definitely excited to get to that. Didn't want to spoil anything, so we'll share it and walk through it. But yeah, one of the things that is nice about entropy is it's very easy to control. So one of the first things that you can think about is adding strings into the payload to lower the entropy. So if you can find definitely where your packed payload's at within the binary, you can start to target that area with a bunch of words such as business words. And what that'll do is it'll essentially start to average out that long array of random characters, and it'll start to bring down that average to something around 4.5 to 5. Also, what we can do is try to store the payload as words UUIDs, and also try to do things, other things that are more space efficient, so it's not as long. And then also storing the payload as an external location is also a valid option. The last one is what you could be thinking of is more of like a stego loader. So essentially what you would do in that situation is you wouldn't have the payload stored in the binary itself, but you would have unpacking code. However, the unpacking code is reaching out to some image that is hosted on a web server. And then when you pull down the image, and that unpacking code knows how to utilize that image to pull the actual shellcode out of it and then load it from there. The reason why that dramatically decreases the entropy is essentially you've now removed it from the binary and it's no longer statically compiled with the binary itself. So not only is that going to be space efficient because the payload that you're sending is now only going to be a couple kilobytes versus a couple megabytes, but it'll also have naturally low entropy. And then this is a funny example that we decided to include in here, but I think it really drives the point home. What you're looking at here is essentially a shellcode injector that is storing its shellcode as Pokemon instead of the bytes itself. So the second line that you're seeing there is a Pokemon array where it has a bunch of different names. And that second blob for loop that you're seeing there is a converter from Pokemon names to actual bytes itself. So effectively achieving the same thing, albeit in a pretty unique manner. Essentially what it's doing is instead of storing these bytes, there's like a long encrypted array that's super random for a long period of time. It's using business words, which are less random and going to lower that entropy for us and achieve that, but then also allow us to store the payload statically and naturally insert business words. So this is a good example of how you can achieve two birds with one stone. And then also, we wanted to show the slide again because it definitely drives the point home of it's not just about the longevity. So you definitely know that this is going to be a packed payload, but it's going to be harder for EDRs to detect because it's going to average out as that 4.5 to 6.0 range. Even though it's still packed and it has a consistent entropy value for a long period of time, it is going to average out to something that we would desire. And then this is the last one. We're going to essentially just give a shout out to, this is not something we came up with. This is definitely a well-known mathematician that came up with this randomness calculation. And then whether or not you want to use ChatGPT or some other type of AI model or find a Stack Overflow article, we essentially just did a bunch of different research to find a Python script that would or a Python blob that will give us the calculation for that Shannon entropy. And then based off results, we compiled those averages, the 4.5 to 6.0, and then started to try to inject our binaries to target that range.
Yep. The link for that measure is there. I think someone asked the question if there was a link to code that could measure Shannon entropy. So there you go. We'll put that in the chat in a bit.
Excellent. And then I will go ahead. I don't know if it'll take over your screen share, but I'll go ahead and try to share my screen here. We do have an exercise that will hopefully drive some of the points that we talked about home. Give me 1 second. I will have to quit and reopen, it looks like. So give me 1 second.
So I'm reading some of these questions. Does EDR only look at the average Shannon entropy value for a file, or does it look at the entropy value over the address space of the file? Both is the answer. So a lot of EDRs are going to be looking at that entropy value as like their golden number to say, oh, if this is 7.8, just kill it. This is definitely malware, right? EDR will probably in the future start to look at some of those graphs. If you look at this slide here with the mitigation, I mean, any human can look at this graph and see there's something wrong with this program. This is not a normal executable, right? And so I imagine in the future we'll see maybe AI or like AI ML stuff, get better and start to look at the actual entropy graph as well, and like understand that this is not legitimate. In the tools that I've written, we've really never needed to do anything beyond, hey, I'm just going to put a bunch of garbage words into the binary, and then that's going to lower the entropy overall. In the future, when maybe some of this starts getting detected, we're going to have to increase the sophistication of our entropy mitigations, so that this graph doesn't look completely, malicious like it does, right? So I imagine that's something that we'll see in the future, but not quite yet in my experience. Yes, there are solutions now that check for entropy. So far, I've only seen them do the number. So it's going to calculate a number like here, right? It's going to say, oh, this is a entropy value of 6.8 or 7.8. That's malware, right? And then it's going to kill those. All right, you back, Skyler?
I am back. I am sharing. I don't know if they're okay. Perfect. Excellent. Thank you, guys. One of the things that we did discuss, so hopefully everybody can see my screen properly. If not, Kevin, yell at me. Is using EXE Spy. This is a wonderful application that we'll provide the link for. That essentially will do a lot of the static analysis that we were referencing. One of the important things is it also has an entropy tab. So that is where we were pulling all the screenshots from. So if you would like to test your own payloads or malware, feel free to download the tool and check it out. So some of the things I have on the right here are a couple of different packed payloads, along with a legitimate piece of malware, along with an actual application that is shipped with Windows. So I'm going to walk through each one of these, and we'll discuss essentially what things that malware would pick off, and what things have changed between each one of the binaries. So for those that don't know, Grouper is a great tool. So shout out to the person that wrote Grouper. They also have an EXE that's just posted on their GitHub that you can download. So it makes it really easy to find malware that is presentable for the purposes of the presentation. So opening up this first one, we will look at a couple things in here. One of the things we did discuss is the timestamp, along with some of the other metadata. So we'll see that one of the things that we can see in here is the timestamp, along with the creation date of the application. Some things that malware will do, essentially, we'll look at recently created files. So think I'm a target for a phishing campaign. I just downloaded a file. It's just recently been executed. So it's a recently executed application. It was created recently. It's living in the downloads folder. It's also not signed. Definitely going to want to start looking into this application for some type of malware. So one of the other things that we can look at, and this one will actually probably look pretty decent, but just to kind of show what a unpacked but still malicious binary looks like, is we can see that high entropy value, but we start to get some drop-offs here at the end that will possibly pull down the entropy. So while we still have these long pieces of entropy for a long period of time at the same value, we will average out into that specific area. One of the other things we talked about is some of the imports, and this is actually not a great example for that. So let me use the other binary that I have here. So I'll go ahead and pull up MSEdge. We'll also be able to see the timestamp information here as well. Thankfully, this works out well, because we're seeing a timestamp of 0417 here, which you would think, oh, this is very recent. Well, it turns out that's when I created the VM. So that's when the binary actually got created. Typically won't always happen on engagements. You'll have other binaries on the system that have been created for a while, whenever the system was provisioned. But one of the more interesting things that we can see here is also the imports like we discussed before. While all these are pretty legitimate because it's MS Edge, and MS Edge is doing typically pretty legitimate things, this is something that EDRs can pick up on and look at. One of the other things that they can look at is also the exports. So we talked about the reliance of signature detection even on heuristic analysis, such as DLL hijacking. One of the things that is pretty common when you're writing some DLL payloads for targeting DLL hijacking is also matching the exports for the DLL. So that's one thing that we can do as well. So not only does EDR look at the imports, but also if you're loading a DLL in some type of malicious manner or trying to target a legitimate application, you should typically try to also match the exports of the original DLL itself, along with hopefully some type of the metadata that we discussed earlier. One thing that is hard but not impossible is also trying to get the binary code signed so that the signature field will also stay verified along with this signer's information, but always not possible. Not a roadblock, but definitely something that can get you over some hurdles if you can get a hold of a valid code signing cert. Moving forward from here, we'll look at some packet binaries as well. So one of the ones that I have here is just called grouper packed. So we'll just jump to the Entropy tab. We kind of saw this already, but this one's a little bit more egregious and definitely going to be caught by malware. What we see here is, sure, we do have some drops on both sides, but we do have a long period of time where we're at 6.5. So this is definitely going to average out above that 6.0 range that we were targeting. Additionally, if we go look at the general tab, we can see that it's not signed, and then we'll be able to see the metadata. So it'll essentially take this along with the entropy value and most likely determine that this is malware and remove it from the system. I shouldn't have clicked out of exe spy completely because now I have to reload it. But now we can take a look at one of the mitigations that we talked about, which is injecting the executable with business words. So this is the one that I have here. Essentially, all we did was we opened up the grouper packed is essentially just a exe with a blob of AES encrypted grouper data, and we take the decryption stub and we decrypt the grouper and then execute it. Now, instead of just having AES data there, it's still there. We also have a bunch of business words injected into it. So we'll take a look at that now as it loads. Hopefully it doesn't crash. Demo gods be nice to me. Give me an entropy tab. Okay, excellent. So we can see that we still have that long period of time where we're at that same entropy rate, but it is much lower, and we could reason to believe that with the entropy that we're seeing here, that will most likely fall between that 4.5 and 6 or 6.0 range. So that is, I think, all for this demo. But yeah, hopefully you guys definitely go take a look at exe spy and start opening up your own malware and start seeing that correlation between entropy and metadata for what EDR can pick off.
Great. All right. I think, yeah, I'm going to do this one. So we're moving on a little bit to the next step in the chain here. So after we have hopefully your entropy mitigations in place and things like, code signing certs or whatever other, your time date stamp is set up the way it should be, right? Then we have to move on to the next step in the chain. So typically when you are, dropping a payload to disk, it's probably going to be packed, right? And so it's usually going to look like some sort of encryption is going to be used on the actual payload data itself. And then that payload is going to be decrypted at runtime and then kind of like loaded into memory and bootstrapped and executed. So on disk here, the screenshot I have is this tool that has some static encryption keys, and then the data itself here on the right is basically these bytes that are encrypted with those static keys. If you do it correctly, this is kind of a bold claim, but if you do it correctly and your payload should not be able to be recovered unless it's executed, right? So the payload is encrypted when it's on disk, and so unless you execute it, it should be impossible to recover. And then we have this concept of guardrails here as well. So in the mind of us red teamers, we really only want the payloads that we generate to be executed on an approved system. So you could think of this like, I make a payload, I only want this payload to work on, you know, whatever your target name domain is. I don't know, I'm not going to make up a name, but, you know, domain.com, it should only work on hosts that are connected to domain.com, right? Something like that. And we don't want it to run on other systems such as sandboxes, which we'll cover in a little bit, or analyst machines, or we just don't even want it to run accidentally on maybe like another client, right? So that's a consideration as well. So, okay, we need to choose some sort of cryptographic algorithm to use to encrypt and decrypt the payload data bytes. There are a number of options here. I'm not going to say that there's one right answer, but what we really want to look for the criteria is, first, we want it to be resistant to cryptanalysis. So if an analyst looks at our payload, they shouldn't be able to brute force the key, or they shouldn't be able to find some sort of weakness in the algorithm to recover the data. So this is going to rule things out like XOR, no Caesar cipher, no, base 64 encryption, which is not encryption. Basically, you need to use something good. So we also want it to be used for legitimate applications. So, what encryption standards are already used, right? What are already in play. And it's kind of a bonus if it's built into the target system already. Given these three, it should be no surprise that AES 256 is a pretty good candidate for this. If you look at lots of software, Python has great libraries for AES. C#, I think, has, actually the code on the right here is all C# code for AES. Many other languages implement AES pretty well. Again, not the only option, but certainly a good one. This is what I've chosen for most of the tools that I write. We just use AES to do that encryption. So far, it hasn't been broken, or it's cryptographically secure in 2025. So that's a good choice. But then we run into this problem, right, where, okay, the payload is packed, it's encrypted, right? But then how does the payload decrypt its encrypted data, right? There's a couple of options. The first option, hopefully you guys can see why this is bad, is we could just put the encryption key inside of the payload itself, right? And then the payload fetches its own encryption key and uses it to decrypt the payload, right? But there's a big downside to that. It's basically like writing the password on a sticky note on a computer. It's, if you include it, it's going to be able to be pulled out of the binary by analysts. And it doesn't matter how secure our encryption algorithm is if we include the key with the encrypted data, right? So great, we can do this, but maybe there's reasons we don't want to do this. And is there a better way to do this? The answer is yes. Environmental keys, this is kind of like the modern standard for encrypting payloads. You don't actually include the encryption key in the payload itself. Now, how does the payload decrypt its data? You basically pre-encrypt the data with values that are already on the host itself. Domain name, username, host name are some really common examples. And then the Payload will fetch those environmental values and derive decryption keys from those environment values. And then those keys are used to decrypt the payload. If, let's say that you key a payload to a host with, host name of workstation 1, and then you move that payload to a host named workstation 2, and you rerun it, well, now the host name is no longer going to be the same. And so the encryption key that's derived is also going to change. And then the payload itself will not be able to be decrypted. Either the program will crash or, it's going to say, hey, can't decrypt exiting or something like that. And so you can see then how the payload is only able to be executed on that one system based off of the environmental keys that are set up that way. You can also get more complex with environmental keying. So you could do some crazy keying where you look at the installed programs or the hardware specs or system boot time or lots of unique fingerprints based off of certain features or a combination of features, maybe even on a host. And that payload would definitely not be able to run on another host, right? Maybe a domain name or a username; those are kind of like weaker keys, but we can key these payloads strongly to a specific host if we want to. Okay, so we get to exercise 3, which is environmental keying. I'm going to write some code live for this, so you guys are going to watch me struggle. Feel free to follow along, though, if you want to. Hopefully this exercise should be doable. Maybe, pull up ChatGPT or Claude or whatever you like using for that. But we're basically going to write some code here to get the computer name. And we're going to convert the computer name to this SHA-256 hash, a value that can be used for keying. And then we're going to encrypt a file with that hash as the key. And then we're going to decrypt the file with the same key. And we're going to compare. If we did it correctly, it should be the same file before and after, right? So let's do that. I'm going to, I actually need, here is some crypto code that has already been written. I'm going to use this. This is Python here. That 2 functions that do decrypt and encrypt. These are wrappers for PyCryptodome Python code. So let's see here. So I'm going to make this new file here. And we're going to try to build this out live. So I have my 2 functions, encrypt and decrypt here. And then I need to write Python code to fetch the host name. So that's the first part, actually. Let's go do that. So I'm going to go back to my browser here, and I'm going to ask ChatGPT, how do I get the computer host name in Python? This is actually how I do most of my programming now. I feel like I don't write code manually anymore. You can judge me all you want, but that's okay. I like having code that works. So I use AI to help me speed this up, but it's great. Okay, so let's try to run this now again. We get the host name. My host name is hackbookpro.local, apparently. So that's cool. I need to convert this into a SHA-256 hash. So that's the next thing I need to do. Can you, how do I convert a string into a SHA-256 hash? Great. So we're going to use this hash lib is the Python library. I think that's built into the standard library in Python. So we'll do that. And we want to take the host name here is instead of s. So it's the host name. So let's do that. And we get, okay, this is the host name, and then this is the value for the hash, SHA-256 hash for hackbookpro.local, that word. And then the last thing we're going to do is we want to, I think I said, encrypt any file with a hash as the key, and then we're actually going to decrypt it with the same one here. So let's see. I'm just going to take a Notepad here. We're going to use Notepad as our target. So Notepad has a SHA-256 hash of this D66, so forth. So we're going to encrypt this, take the bytes, decrypt it, write the bytes, and then we're going to compare. It should be the same hash, meaning it's the same file after we encrypt and decrypt it. So let's see here. So we should just be able to call encrypt and decrypt here. So we'll do I think I need to do something like we need to read the file. So with open notepad.exe, I need to read the binary file here. So we need to read this data in here. And then let's just print the data afterwards to make sure that this is correct. So there you go. That's the whole entirety of the Notepad data. Great. And then we're going to do encrypted data and then do encrypt. I think I can do, I don't know if I need the bytes object here. So let's try this. This is not going to work, but we basically want to put the hash in as the key, and the plain text bytes, that's going to be the data here from the Notepad file. So let's try this. I don't think it's going to work. It needs a AS key length of 64 bytes. So okay. Oh, 32 bytes, not 64. Interesting. It needs to be 64. Oh, actually, I think it should have been a SHA-512, probably, is what I meant. That would be 64 bytes, I think. So, but we'll just do it this way. Great. So, let's do this. Host name hash equals SHA-256 bytes, and then we put the host name in there. And then we want to do host name hash here. So basically, we're taking this hash and using it to encrypt the data. I got an error. It says encrypt key 64 bytes. I actually might try this. So, yeah, I think I typoed the exercise. This should have been a SHA 512 instead. Nope, it's still not working. Okay, I might scrap this exercise, unfortunately, because I can't. I'm not going to take the time to do it live, but basically this concept here does work where we want to find the host name of a specific host. We're going to take that and turn it into a hash or something that can be used as a key. And then we're going to use some sort of encryption algorithm with the key that's derived from the host name to encrypt a blob of data. And then basically using the same key to decrypt the same encrypted blob of data to get the original data out. So apologies, I should have had that working, but I'm not going to spend too much time on it just for the sake of the rest of these slides. So, yep. Okay. We're going to move on with the slides here. I'm going to talk about, by the way, if anyone does get that working, let me know. It'd be cool to see the solution if anyone was able to get that exercise completed. But moving on here, we're going to talk about sandboxes. So we're getting into the next step in the chain. We are assuming that the payload was decrypted successfully, and that payload execution is continuing here, right? We have another hurdle though, which is sandboxes. So let's say that you send a file to a target and they execute it on their system. That same file might actually also get uploaded to a sandbox, and prior to execution, or maybe afterwards, your payload might be executed inside of the sandbox, and then thus kind of showing your hand about what the payload does. It's going to look at things like your network connections of the payload, things like files or registry modifications, API calls that the payload is doing, or like process creation, right? If it spawns any programs underneath it. All of these things can give away what your payload does. And so ideally we want the payload to not run inside of a sandbox. So there are a number of anti-sandboxing techniques we can do here. So we could, look at the system memory. A lot of sandboxes have really low memory, right? Because they're not actual machines. Could look for things like presence of a fan or certain hardware that might actually only be present on real systems. Screen size is a really funny one. This meme here is from an actual malware sample that was discovered, which was did some anti-sandboxing, and if the screen resolution is less than 1280, that's not a real computer, right? And so it just exited, which I think is really funny that this actually worked for anti-sandboxing stuff. But sometimes it's the simple things that work well, right? So we can also do long sleep or delays before execution. So if you think about a sandbox, it's only going to run for so long. So you could sleep for 2 minutes or something before the payload executes. You could look for installation of common programs. So if the sandbox, does not have Chrome on it or something, that's kind of weird. most systems have Chrome on it, or recently created or modified files. So, if it's a real system, the user is probably going to have some files that are on their desktop or something that have been modified in the last, I don't know, month or two, or other locations, right? So sandboxes may not update those files regularly, or they might. But we run into this issue where, this sandbox developers kind of know these things. So we get this this cat and mouse game where anti-sandbox techniques are known, and there's anti-sandboxing techniques, right? So these sandboxes will try to emulate things like hardware or installed programs, files, screen resolution. Specifically, they can also emulate or fast forward sleep or time delays. So that's, some of these techniques don't work as well anymore as they used to. But then really at the end of the day, the attackers still have the upper hand here when it comes to sandbox evasion. Sandboxes can't fake certain things. So like real CPU execution, long computations, and math are a couple of big ones that you can't really emulate that. That has to be performed for real, right? You can't fast forward math. You can't, it doesn't work that way. So, and then sandboxes have this maximum runtime too. So eventually, if you kind of run your payload long enough, the sandboxes will time out and just kind of give up on it. So that's a good way that I like to use personally to kind of evade these sandboxes is, what if you just do math until it gives up, much like me in high school. So that brings us to the last slide in this section, which is emulation. Sandboxes are used a lot for manual analysis, but when we talk about automated defenses, you don't really think about sandboxes too much as like, oh, like my payload's going to go into a sandbox, right? But EDRs actually do a lot of sandboxing. The term that we use is payload emulation. So it's basically a sandbox that exists on the same host as the payload. And so EDR will kind of like put this payload that you have in the twilight zone for a little bit, execute it, see if it does anything malicious, and then if it doesn't, it's going to allow it to be like executed for real. And then if it does, it's just going to kill that process and delete it, or like exit the emulator, right? So some of the details about the host are going to be the same. So like the username and stuff, and the computer name is going to match what you would expect it to on the host. It's not going to be like a sandbox username or a sandbox host name. But then we still have the same limits for the emulator, where there's a certain amount of time that's going to be emulated, number of instructions, the API calls, and then there's like a max memory that can be used for an emulator. And so if we can exceed these limits, we'll basically time the emulator out and basically escape from the emulator into like a real execution context. So that brings us to our fourth exercise here. We're going to have Skyler demo that one for us. See, Skyler, are you there?
Yeah, I'm here. I'm trying to make sure that I share my screen in a better fashion this time.
Okay. Maybe, yeah.
Let me see. Okay, so share my entire screen. See if I can zoom in here. Is this better and more legible? Let me know once you can see my screen, Kevin.
Yeah, looks good.
Awesome. Excellent. Like Kevin mentioned, there are some limitations on sandboxing. Obviously, they can't go on forever. They can't sandbox your process forever. So one of the things that I have here that also last minute modification. So we'll pray to the demo gods that everything works well. But we have a little bit of a simulated EDR here. Essentially, what it's looking for is recently spawned processes. Where it'll just print out saying, hey, we're looking for malware. It'll look for what creation time the process was. And at the end of the day, we'll look to see if the process has had the same process utilization for a long period of time. One of the other things that it'll do is it'll also check to see if this file has been written recently. This is kind of simulating some type of detection being written for known malware. In our case, it's just pwn.txt being written out to a file. But essentially, if within a certain duration, this heuristic has occurred, then it'll essentially flag it as malware. So for anybody that's interested, I'd be more than happy to share my my fake EDR here, but we'll go ahead and run it. So now that the EDR is running, let me go ahead and zoom in here. We also have 3 different types of malware. Let me go ahead and remove pwn.txt for now. The first one here is going to be some simple malware. Essentially, it's doing really nothing other than you could think of this as like the shellcode injection or DLL hijack, where it's trying to execute that malicious code. And if everything goes well, we'll run this and we'll come back over here. And ideally, if it's not going to blow up in my face, we'll give it about 5 to 10 seconds, and then we'll see if I can get it working. But it would check now within the next time frame window of the process spawning if it had written that file. It looks like that should have already popped. So give me 1 second. The change that I made was not a change that should have broken that, but that's typically how demos work. So let me go ahead and rerun that real quick. Let me go ahead and reset this. Make sure that it's running successfully. I'll remove that and we'll rerun it again. And thank the demo gods, it definitely found it. So now within the given time frame that the process had spawned and written or done the heuristical action that the EDR was going for, you could think of this as also just a slew of detections. So you could have, let's say, just a bunch of JSON files that have the action being file write or file read or modify registry key. It'll essentially loop through all of those for newly spawned processes. Other things like shellcode injection, such as creating read write execute memory. All of this falls within that same category. Just in our case, it's pwn.txt. One of the things that is particularly interesting, and I'd like to show, is that pwn.txt actually still gets written out. This is very common, and sometimes something that is just on the operator to decide whether or not it's operationally acceptable. While we still have an alert, sometimes the alert, in this case, there's no medium or high or critical severity here, but sometimes the alert is so low where it's just throwing a low or a medium, but also still doing our action, albeit it killed it after it already had written the file. So we'll take that into consideration on whether or not we're far enough into the engagement where our OPSEC profile is now, higher because we're getting to the end of the engagement where we're allowing things that we need to work but are going to throw alerts, and we just take that into consideration while we're operating in that. But coming back to sandboxes, we'll go ahead and rerun the EDR again. I just got to make this a little cleaner. One of the things that you could think to do at the beginning of trying to bypass EDR is adding some type of sleep. So what happens during that first window? Let's not do anything. Let's just sleep. Well, like we've kind of discussed before, we're going to run this because it'll take some time. Is EDR will essentially analyze newly spun processes for things that it's doing, like the the shellcode injection, like we discussed before, but also common sandbox anti-sandboxing techniques such as sleeping. So now this malware will essentially attempt to try to bypass the sandbox by just sleeping and then doing our our fake shellcode injection. But if all goes well, we'll see within that time frame window that the DR will pick it up that this process has maintained this similar CPU utilization, and then kicked it for evasive behavior. So we see that alert come by, and we see it killed successfully. And then finally, I'll go ahead and rerun the EDR again, and then switch to this last window. Why I have separate windows for this now that I'm thinking about it, I have no idea, but that's just what fit well in my mind. We have this last malware, and I'll go ahead and cat it out so you can see it. It is using some type of computational delay. Essentially what it's doing is it's still trying to check the duration. You could do some like pre-analysis on the computation you're doing to know that doing this amount of square roots will take a second, and then you just rename the function to sleep second computationally. In this scenario, I just have it set to, hey, are we to that estimated duration window that the sandbox is trying to identify us? If not, do more computation. Not the best scenario, because some of these API calls to even check what time you're going while you're doing that, iteratively, is also suspicious. But for the purposes of the demo, will fit our EDR. So we have it running over here. So I'll go ahead and run it. And it will take 60 seconds to go out, but ideally with the computational delay, we will successfully bypass the cheap Skyler EDR.
Sweet.
Go ahead, Kevin.
Oh, keep going.
I was just going to say there are also other things like we mentioned, not just computational delays. You can also add in things such as different API calls that actually will break the sandbox, so it'll just exit your process, be like, I can't emulate that. So think of things as such as like a container that is trying to execute your sandbox. Sometimes it can't call certain APIs. Sometimes it's not built for the right architecture. So you can actually leverage that in your favor so that it will then just not even try to emulate your malware, and you can bypass it that way as well. We are not just limited to the fact of just doing something until it gets past that window. But now that we can actually look, and we have our pwn.txt file written out, and hello RTV is in the contents here. So that is it for me, and I will pass it back off to Kevin.
Great. All right. Let's move on here. So, okay, we get to the next step in the chain that we've been going through here. So we're talking about, all right, our payload decrypted successfully. It was able to, do some sleeps or delays to evade sandboxes or emulation. Now we get to the point where the payload data actually needs to be loaded into memory in some form or fashion, and then executed, right? So typically you'll see this categorized as reflective loaders.
Kevin,
Yep.
sorry to interrupt. Question popped up here. I think maybe this is more when Skyler was talking, but question popped up. Are you doing any polymorphic tricks to make payloads different for each build?
That's a great question. Yes and no, actually. There's nothing special you need to do, but if you just use, if you're doing, for example, like AES encryption, when you generate encrypted payloads, you're going to have an IV, which stands for initialization vector. It's just a random value that's it's random for every single time you do encryption or you generate a new key. And that random IV is going to change the way the encrypted data looks when it's in the payload. So we can generate 10 payloads with the same keys, but then the IV is going to be different for each payload. And so the encrypted data inside of the payload will be different for each payload. and then the overall the hash will be different for each payload. Yeah.
One thing we've also discussed as well is we have our C# packers as like templates essentially, and we've discussed trying to like templatize the variables within those templates so that they would change every time as well, so they're not just static method names. We haven't had to do that yet, but definitely something as well that you can use to kind of change up the packer even, not just the encrypted code.
Nice, cool.
Yep.
Thank you.
Yep. All right, so yeah, we're going to talk about reflective loaders for a bit. I'm going to group them up into 4 different kinds of reflective loaders. Maybe there's more, but these are the big ones. Conceptually, shellcode loaders, DLL loaders, .NET assembly loaders, and then beacon object file loaders. These all are similar-ish, but there's some nuances. If you're making a payload tool, it's actually pretty nice to support multiple of these. There's oftentimes when someone says, hey, can you pack up a payload for this .NET assembly? And I say, oh, sure, yeah, we can do that. Or, oh, we have to have shellcode. Like my tool only outputs shellcode. Can you pack shellcode? And I say, sure, I can do that. Because they're, the way that I've written some of my tools, it has options that you can choose shellcode or DLL or .NET assemblies and so forth. So good to support as many input types as you possibly can. My values for a loader, I think if you're making your own loader, here are 4 criteria that I would look at to build your own loader. I think first and foremost, loaders should be stable. Nobody wants a payload loader that crashes half the time or a quarter of the time. That's absolutely frustrating. It should work every single time, and it should work on different operating systems. Windows 10, Windows 11, Server 2019, and so forth. It should work on everything. So stable. Unique, obviously, we talked about static signatures. Payload loaders are exposed during the execution process, right? We have our packed data, but the payload loaders, these things also need to be a lot of times uploaded to disk. So static signatures apply, and so they need to be unique and not signatured. I believe they should be simple and small as well. I think payload loaders are kind of this piece of code that oftentimes you just need to rewrite a couple of times because, oh, my payload got put in a sandbox and now my payload loader got signatured. So I have to rewrite a whole new loader, right? That's pretty common. So, if your payload loader is really complicated and took a whole bunch of time to write, it might take a long time to rewrite it, and just expect that you're going to have to rewrite multiple of these payload loaders in the future the next time your loader gets burnt. So, okay. So process injection, specifically for shellcode loading, we run into basically 3 items here for shellcode injection. So just in general, we need to allocate a buffer of memory. So we say, hey, operating system, please create some memory for me. And then the second thing is, after we have a memory, memory created, we need to copy our shellcode into that memory. And then finally, the third thing is we need to run that location of memory. So I have some API calls here that will do those things, but there are other API calls that will perform the same conceptual actions, right? So, hey, you actually don't need to do create thread to run memory. You just need to either convince another part of your program to do create thread for you, or call execution on that memory yourself. There are a couple ways to do these things, right? So here's your basic injector in C. Again, short, simple, small, right? And this is probably pretty reliable. This is going to get caught because this is your vanilla shellcode injector, but conceptually, I want you to see here that there are 3 steps. It's the virtual alloc, the allocation of memory, the mem copying the memory, and then creating a thread. It's the execution. So once we understand that this is a 3-step process, we can go through and start making it more complicated or doing evasion things on it to make it look different. So memory permissions on Windows. This is kind of an indicator, something that I want people to be aware of when they develop their own loaders, because memory permissions can get you caught, and there's some gotchas here. So in general, memory permissions are either readable, writable, or executable on Windows, and then or any combination of those. So you could have like read-write memory, read-write execute memory, read execute memory, or even memory that has none of those. So like nothing, basically, right? Mostly when you like, a lot of memory is allocated when you just allocate memory by default, it's read-write. So the operating system thinks that you're going to use this memory to store things like data structures or I don't know, binary blobs of images or things like that in memory. And so you won't be able to directly execute memory that you allocate. You'd have to use something like virtual protect to modify those memory permissions in order for them to be, read execute or read write execute or things like that. And so that brings us to some evasion, right? So we have a couple options. If we're trying to write shellcode into memory and then execute that virtual memory, we have a couple options. First, we could specifically allocate the memory read, write, execute. Again, because we need to write the memory into it, and then we need to execute the memory. Or we could allocate it as read, write our memories, or write our shellcode into the memory, and then flip the permissions to read, execute after copying the shellcode. That's also an option. Or then we have option 3 here, which is we can allocate memory as read, execute, flip it to read, write the shellcode into the buffer, flip it back to read, execute, and then execute it. If you didn't already know, there's another API called virtual query that can be used to check the memory permissions of memory as they were originally. So if you have memory that's like it's read, execute, but it originally was read, write, that's pretty uncommon, and EDR will look at that and say, why is this memory changed to read, execute? That's strange, right? So I think option 3 is probably the best in terms of if we're just going to do sort of standard shellcode injection. But there's still those indicators like you're using virtual protect to modify those memory sections. This brings us to another concept here. Most processes don't really have very much read, write, execute memory by default. EDR will look at memory that's read, write, execute, and kind of it's like, that's probably not legit. Like, especially if it's in a unmanaged process, like a process that's written in something like C or C++. Seeing read, write, execute memory is kind of an indicator it's bad. But then we have all of these like managed languages that do that have read, write, execute memory everywhere. So if you think about something like Java or Python or C# or Node.js, PowerShell, these are all kind of scripting languages or dynamic programming languages that will often use just-in-time compilation to make their execution more efficient. And so you end up with a whole bunch of read, write, execute memory in these processes. We can take advantage of that. So Skyler, do you want to do the exercise 5?
Will do. Can do. Give me 1 second. Awesome. So let me know if you can see my screen.
That is probably going to be illegible on the YouTube stream because
so.
the resolution is so tiny.
Let me go and stop sharing again and just try to share. Is there an option for... Let me try to put it on the same screen. Can I split screens here?
Does your OS have an application zoom level? I don't know if that would work.
Actually, let's try that. And now, where did my... Yeah, there we go. Do it live. So I have this now zoomed in. Can you guys see this all right?
Let's see. That will probably be better. We'll wait and see if we get any other feedback.
I don't know why it's not, or it's like super pixelated, but I do have it zoomed in here now.
Okay, yep. Folks are happy.
Excellent. Yeah, so what we're taking a look at here is System Informer, previously known as Process Hacker. This is now available in the Windows Store, which is great. But one of the things we're going to take a look at is some unmanaged and managed processes. So taking a look at, I think we could just click on explorer.exe here, if I can find it. There we go. One of the nice things about Process Hacker is that we can pull up a variety of things about the processes in memory. So we talked about exe spy, and it's talking about essentially we got it on disk. We're looking for detections. What things can they see? Well, now EDR has allowed us to be in memory. What things can they see in memory now? So there's a variety of things that they can see. They can see our original command line that was executed for the process itself, along with whatever parent process and architecture that we started up with, when the start time was. So we saw my fake EDR we were using if the process had started within the 60 seconds or last 60 seconds and did this. That's something that will very commonly happen for processes. Some of the other things that we can see here is also just, what threads are provisioned and what permissions they've been provisioned with as well. Something very nice to see when you're looking at legitimate processes running on the system. The other tab that we have access to is this memory tab. This one's in particular for this set of slides interesting because we can see what kind of protection mechanisms have been put on the memory pages inside of the process that we're analyzing. If I go ahead and scroll through here, we'll see that we have some read execute, but we'll notice that we don't really have too much read write execute. So through our analysis, we found that most unmanaged processes, it's very uncommon for them to provision read write execute memory. This is essentially the best way to think about managed versus unmanaged is whether or not the process needs to be ran by some runtime. So think of the .NET runtime. Essentially what happens is the code gets loaded up into this runtime, gets converted into some bytecode, and then is ran and provisioned and has some type of garbage collector with it to be able to host the process. Well, with that, it basically provisions a bunch of different capabilities. And one of those is an efficiency capability known as just-in-time compiling. So if we go ahead and take a look at this PowerShell process that is actually a .NET process at heart, and scroll through the memory tab, which thankfully it's opened up for me. We can scroll through here and we will very quickly see a bunch of read write execute memory. The reason why it does this is because it's essentially taking code and writing it up as if we were doing shellcode injection. It's as a legitimate functionality, and it does this so that it doesn't have to continually load that and execute that. And if it identifies a method or a coroutine has been executed multiple times, it'll essentially take that, throw it up into a page, and that it'll be more efficient to execute. This was nice for us as attackers because if we write our one, there's legitimate processes that are managed on the system using read, write, execute memory, so it makes it a little bit more common. But also, if we target our payloads towards something like C#, and we're using read, write, execute memory, we can kind of blend in a little bit. And then finally, we can actually take advantage of the legitimate functionality of just-in-time compiling. So if you can trick the .NET runtime into compiling or provisioning, this read, write, execute memory, and you can get the handle to it, you can actually leverage it yourself. So if you can try to find some way that will essentially, you could call the coroutine a bunch of times, but there's also exposed functionality through the .NET framework that allows you to just say, hey, I want this one to be JIT compiled. It will then provision redirect execute memory for you, and then you can leverage that to do your shellcode injection. So there are other functionalities that do something very similar, but just to get the wheel spinning, this is something that has been leveraged pretty recently, and yeah, definitely very interesting.
Sweet. All right, we got a couple more slides left and a couple more minutes, so I'm going to try to get through this. Feel free to ask any questions in the chat. We'll try to answer them along the way. So, but hopefully I should be pretty much finished with these slides by the time we reach the top of the hour. So, okay, so next link in the chain, right? We did all of our evasion stuff, and your shellcode gets put into memory, right? Executes. The EDR is not done yet with us. There are tools called memory scanners, which is going to look at your processes running memory, and it's going to do it's going to look for suspicious things in memory. So a lot of these are signature based, so it's just looking for things like, oh hey, there's the Beacon DLL program running in memory, or a Metasploit DLL running in memory. Like that's evil, right? So signature based. Things like PE or DOS stubs or headers in memory, like that probably shouldn't be there. Those things. The good news for us is EDR can't scan all the processes all the time. It takes a lot of memory to do, or a lot of CPU resources to do this. So it's only usually triggered after maybe some suspicious event like flipping memory permissions or something like that, right? So here are two great tools that you can use, Monita and PEsive, if you're trying to do your own memory scanning. So you can see that there's this DOS stub in memory on the right screenshot, and you can see that I think this is Monita. No, PEsive discovered that, hey, there's an implanted PE in memory, which makes sense. Like there's a DOS stub in memory. So yeah. And then there's two ways around these memory scanners. First, if you're using an implant with unknown memory signatures, so you can rule out Meterpreter, Cobalt Strike, Brute Ratel, Nighthawk, etc. If you're using an unknown implant, memory scanning isn't usually an issue because, well, there's no signatures for your implant in memory. So if you're looking at something like a sleep mask where your payload has to have code that's going to encrypt its own machine instructions in memory while it's idle, and then it's going to kind of unhide itself between those beacon cycles when it wakes up. So couple more gotchas here. Unbacked memory regions. By default, when you load something like a DLL in a process, that DLL is going to exist on disk and in memory at the same time. If you have code that's on disk, or excuse me, in memory, but it's not on disk somehow, that's called an unbacked memory region. And typically those are either, you'll see those in dynamic processes that are like C#, Java, Python, etc., or that's probably injected shellcode. So something to be aware of there. Unbacked memory regions. You can get away with it if you use like a managed process, for example, C#. I'm going to skip these process injection slides. Here, I'm not going to talk about this too much, but Here's a couple of examples of some reflective loaders if you are interested in going actually to take a look at some of the code to do these kind of reflective injection loading things. So, and I am not going to get to do my last demo. I wanted to show off a tool that Skyler and I have spent a long time writing called EK47. It's out there publicly. A lot of the research that has been done in the slides here has already been implemented into EK47 for you. So, for example, EK47 will manage your entropy for you. It's going to handle changing the time date stamp. It handles encryption and environmental keying. A lot of the things that we talked about in these slides for you. So, yeah. And then I'm going to skip the prevention slides as well. I feel like this is less important. As a red teamer, we're mostly interested in, getting in. If you have to talk to your clients about how to prevent these, though, there are some things. We find application whitelisting being probably the most effective prevention for a lot of malware, evasive malware, right, that gets run on hosts. So that's it. Thanks, guys, for your time, and I didn't want to go too far over. So here's Skyler and I's Twitter profiles if you want to follow us or you care what we say online. I don't know. And then we have a link for EK47 as well, which is this tool that Skyler and I have written over the past couple of years. So with that, that's it. Do you guys have any questions on any of the material or anything like that?
I think we had a lot
It's
of
way
good
too big for
questions
me.
already. Oh, yeah,
Make me smaller.
There's Mike. There we go. Wrong button. Yeah, no, we had a lot of good questions. I think we pretty much answered them as we went along. I don't know, Desync or Mike, do you think we missed any questions?
Not that I noticed specifically that came up during the talk itself. We'll give it another minute here for any last minute questions to filter in.
Yeah, seems all good.
Hey, if you guys end up coming out to DEF CON, maybe you can submit that last little exercise as one of our tactics to show off. Let people come and continue off where you weren't able to complete there.
Yeah, if you guys want us to demo that, let us know.
If you're going to be out, we would love to have you guys stop by. But
Absolutely.
I honestly learned a lot. I haven't done a lot of the malware type of development and the evasion types of things. It always seemed a lot more complex than the way that you guys broke it down today, at least from my perspective. So that was super enlightening for me. So I appreciate you guys taking the time to explain all of those things. And I liked some of the crypto stuff. Like that's what really got me into security and CTFs and all that. And thinking about how you can protect that encrypted stuff without giving away the keys too. So like using those environmental variables and those types of things was an interesting way to be able to unlock it without really letting somebody know, unless they're following it step by step to unlock that and to run it. So that was really cool.
Yeah, it's great to hear. Hopefully it should be more simple, right? Than when you think about it, like you think it's really complex, but if you break it down, hopefully it should be pretty simple, step by step.
Also, I do a lot of my coding the same way, Kevin, so you're not alone.
Perfect. Good to know.
It just replaced Stack Overflow pages.
for real, yeah.
Yeah. All right. I think we answered all the questions. I want to say thank you again to Kevin and Skyler. Hopefully, maybe you'll see EK47 as a tactic at the village. I don't know. We'll see. Hopefully. But I just want to say thank you again. RedTeamVillage.io, volunteers, sponsors, workshops, tactics, everything's open for, I think, another 2 weeks. All right? Yeah. Thanks again. Kevin, Skyler, any last words before we blow up the speakers of our listeners with our outro video?
No, go for it. Thanks for having us. Appreciate it.
Really appreciate it. Thank you,
Thanks
guys.
for presenting.
Yeah. Thanks, guys. All right. You've been warned. Goodbye.